I recently came across this paper titled Transformers Without Normalization, and it's quite interesting because normalization layers are quite ubiquitous, as in they are one of the fundamental building blocks of modern neural networks. And if you take a single block of a transformer neural network, we can see that there's layer normalization right there, and it's one of the essential building blocks of transformers. And what this paper is saying that is that we can simply replace this layer normalization with a new block, which is called dynamic tanh. Just by doing so, we can perform as good as a transformer block that has normalization, or in fact, we can perform slightly better than the transformer block with normalization. So in this paper, let's deep dive into this dynamic tanh and understand how it's implemented and how a transformer block is affected by the introduction of this dynamic tanh. So the story of normalization in deep networks dates back a decade actually. So it all started with batch normalization that was introduced in 2015 by Sergey Yoffe and Christian. The paper title was Batch Normalization: Accelerating Deep Neural Network Training by Reducing Internal Covariate Shift. So the idea is that if you have the input features which are xi, then you can compute a mean over it, and then you can also compute a standard deviation of it, and you can always subtract the mean from the input. You can also divide by the standard deviation, which is the standard normalization approach. And following the introduction of batch normalization, we had layer normalization, instance normalization, group normalization, and root mean square normalization. And it's usually this, like the layer normalization and root mean square normalizations, that is used in most of the recent transformer architecture. Even if you take sophisticated models like your latest GPT models or DeepSeek, it's going to be either one of these two that are being used. So if we try to understand them, this figure from the group normalization paper does justice to it. Just one figure will help us understand all the four ideas. So if you take batch norm, you have the input. This is the case of images. We have the height and width, and we have the channels, and we also have n, which is the batch size. If you want to normalize in this direction, which is the mini batch size, then we have the batch norm. And if you want to do the normalization in the direction of C, then we have layer normalization. At the same time, if you want to do the normalization just for one instance, just this, despite having so many channels, then you arrive at instance norm. Then you have group norm, where you do normalization not across the entire channel, but you just take part of the channel and you just normalize that one. Then you arrive at group norm. So the literature on normalization is quite rich, and it's deep rooted in the deep neural networks architecture. No pun intended here, but it takes a lot of guts to kind of say that we don't want any of this and we can live without all of these. If it came from any other lab, I would have taken this with a grain of salt, saying that, this idea is not going to work, but it comes from two biggies in the field. For example, we have Kai-Ming He and Yann LeCun. Both are highly respected people in the field of computer vision, or AI for that matter. So definitely this paper is worth the read. So before we jump into understanding what this dynamic tanh is, let's start with some background and understand what the normalization layers are. So if you take typical normalization, we have the mean that is subtracted from the input, and we have the epsilon, which is a small constant in order to avoid divide by zero. So in case if this is very small, then this is going to be divided by zero, and this entire term is going to be blow up to infinity. So in order to avoid that, we add a small epsilon, which is a small constant. Obviously, we have the standard deviation that is going to divide the input. And in order to make the entire thing learnable, we have two learnable parameters, which is gamma and beta. And these two are the parameters that are going to be learned, and they're called the learnable vector parameters of shape C, and they're also referred to as the scaling and the shifting parameters. This is how a typical normalization equation looks like. And obviously there are different variations like the batch normalization, the layer normalization, and root mean square normalization, everything that we just discussed about. But what exactly is going on in this normalization layers? So to understand that, what they did in this paper is they took the vision transformer and diffusion transformer, and they took the outputs of different layers, right from early layers like the layer 5, and they went all the way up to layer 13, layer 21, and layer 28. In case of vision transformer, they went up to layer 25. Basically, they examined what happens if we go deeper into the network, and they observed something interesting. So in the early layers, the output is quite linear. You can see just a straight line here, but as we go deeper, this becomes more like a S-shaped curve, which resembles that of tan H. You can see that there is a typical behavior emerging. So if we go further deep, we can see that there's a S-shaped curve emerging. And this motivated them to kind of use tan H in place of normalization. So what is this tan H curve? So if we take the tan H curve, we can see that this is a typical tan H curve. We have this S shape, and it ranges from +1 to -1 at the output as we go from 0 to positive X or 0 to negative X. So it tries to squash the output between 1 and -1, irrespective of how much away you go from 0. So even if you go to, +100 or -100 on the x-axis, the output is going to stick with 1 or -1. So that's the main idea of tan H. And they've introduced a small parameter here, which is alpha. As we change the value of alpha for 3 different values of alpha, we can see that we get 3 different curves with different slope. For this one, this is the value with alpha that is 4H, that's very high, and this blue curve with alpha is just like 0.25. So we can see that as alpha decreases, it becomes much flatter, but as alpha increases, it becomes like a very steep kind of curve. And that leads us to dynamic tan H, basically. So if we go back to the normalization equation now, we can see that we have replaced the normalization with this tan H, the plot of which we just saw. And we have still the learning parameters, gamma and beta. But instead of normalization, if we just drop in tan H of alpha X, where alpha is going to be your learnable parameter, then you have 3 parameters now to learn, but then you arrive at dynamic tan H, which is the main idea of this paper. So let's look at the pseudocode here. It's a nice little PyTorch class they have given. So you have the dynamic tan H. You initialize 3 parameters, which is alpha, gamma, and beta. You initialize alpha with some initial value. In this paper, they have taken 0.5 and they're advising to stick with 0.5. And if you take gamma, it's all going to be ones. And if you take beta, it's all going to be zeros. So we're going to start with gamma of 1. This one's going to be 0.5, tan H of 0.5, and this is going to be 0. And we are going to be using the dynamic tan H as a drop-in replacement. So this module is going to be a drop-in replacement for any normalization layer that you have in your network. Could be a transformer or it could be a convolutional network, and they do replace it, and they change the model architecture, and they experiment with transformers and few other modern architectures across a diverse range of tasks and domains. For example, they do supervised learning on vision, and they train a vision transformer and a connex network, both for the base and large size on the ImageNet 1K classification task, and they have reported the results in table 1. So let's have a look at that. So if we look at table 1, we can see that with the layer normalization, with the vision transformer base, for example, we achieve 82.3. But with dynamic tan H, we achieve 82.5. That's an increase of 0.2% in terms of accuracy. And the same is observed for connext. We can see that we are either matching or we are improving in terms of the accuracy with the dynamic tan H. And they also experimented with self-supervised learning in terms of vision. And they have used the Dyna model for it. And they have fine-tuned it instead of training from scratch. And they can also observe that the performance either sticks to using layer normalization, or we notice slight improvement in terms of the accuracy. Also for the diffusion transformers, they have experimented with the base, large, and XL size on ImageNet 1K, and they have reported accuracies And we can see that we can live without the layer normalization layer, and we don't see a big change in terms of the output performance. So having reported those results, they also move on to some analysis or ablation studies. And if you take the dynamic tan H, there are only two. Basically, we have tan H or the alpha, which is the learnable parameters. They try to ablate on both of them. For instance, they try to replace the tan H with the hard tan H, and also a sigmoid function and even an identity function. And in all three cases, they found that the performance could not match that of the tan H. For example, we can see here that in a vision transformer small, the tan H function leads to accuracy of 80.3, but that cannot be matched with that of the identity function or hard tan H or the sigmoid function, indicating the significance of using tan H instead of any other non-linearity functions. And they also study the importance of the learnable parameter alpha, and show that with alpha, it doesn't matter what the nonlinearity that you use. With alpha, the performance is better, be it tan H or hard tan H or sigmoid. The performance improves, indicating the significance of alpha. So you need both tan H and alpha that are part of the dynamic tan H. Otherwise, you're not going to get good performance. So even though they have done the ablation and understood the significance of tan H and alpha, they haven't compared with other methods. So they go one step ahead and compare with other methods that try to remove the normalization layers from the transformers. There are two categories mainly. There's initialization based and weight normalization based. So these two methods, fix up and skip init, or more of initialization based methods. And sigma reparam is that of a weight normalization based method. In all their comparison or all their experiments, they found that dynamic tan H seems to outperform that of the previous methods that are not normalization based. And next comes the initialization of alpha. So as alpha is a trainable parameter, we need to initialize it to some value. They have shown in this plot that it really doesn't matter the initialization. If we do different initialization for alpha, the performance is not varying that much. For example, we can see a flat curve here, we can see a flat curve here, and similarly other ones, there's only a slight variation for any value of alpha that we have chosen. The only exception being that of a vision transformer large, where the initial value of larger than 0.6 seems to have a slight impact. Talking of the alpha 0 or the alpha initialization, they say that higher values for attention blocks seems to improve the performance. For example, if you take the LLAMA model, it doesn't matter the size of whether it's a 7 billion or 70 billion. They are advising to initialize with 0.8, for example, for the 7 billion. If it's the attention layer, but for the other layers, you initialize with a smaller value of 0.2. Similarly, for the other LLAMA models, a larger value for the attention, and for all other layers, it's a smaller value for initialization. A larger one, which is 0.2 for the attention layer, and a smaller one for initializing the other layers. That's across the board if you're training any LLM. And after that, they've just reviewed some related work, and they are simply concluding with some limitations. So that's a nice little paper with a simple idea which can be quite powerful in the future transformer models or for the future models that are yet to come. And I can't wait to see what models make use of the dynamic tan H. Until then, I'm signing off, and I will see you in my next video. Take care.